And welcome back to the Glenn Gerberg Weather and Climate Summit. I'm Dave Jones, the CEO of Storm Center Communications, and we're going to get right into our next speaker. Dr. Lora Koenig has traveled the world studying ice sheets, has been up into Greenland and also in Antarctica. And some of the visuals and information she has will be fascinating. Please, if you're watching online, if you have any questions you'd like to submit, please feel free to submit them through the live Ustream link, or any of you watching through your TV station, local meteorologists that are here in attendance, feel free to tweet those questions out as well, and we'll get those questions answered. Once Dr. Koenig finishes with her presentation, we're going to take a few-minute break, and then we're going to bring both Dr. Tim Brown and Lora Koenig back to answer your questions live through the internet. So it's a great opportunity for you to ask questions directly as well. So with that, I'd like to introduce Dr. Lora Koenig and take a look at her video on Operation Ice Bridge. Let's take a look.
The ice is melting. The seas are rising. Little by little, in most parts of the world, the ocean is overtaking the land. Most of us don't think much about sea level rise, but it's one of the biggest signs that humans are affecting the Earth's climate, and it's something worth watching. So the big question is, are we facing a doom and gloom scenario?
I prefer not to think about climate change and global warming in terms of doom and gloom scenarios, so much as a change in our planet. Our planet's definitely changing, and we're definitely causing it. So we're going to have to learn to deal with some of these changes. But in addition, we're going to have to learn how to make a slightly smaller footprint on our planet. Sea level is rising effectively because of global warming. As the planet heats up, then two things happen to the ocean. One is that the temperature of the water increases, and as that happens, the water actually expands and takes up more room. The other thing that happens is that ice that was on land in the form of glaciers and ice sheets begins to melt, and as that runs off into the ocean, it increases the water in the ocean, and it actually raises sea level as well.
It's important to understand how the world's ice sheets form, how they change over time, and how fast they are moving into the sea. That's where researchers like NASA's Lora Koenig come in. She recently spent 3 months in Greenland studying the composition of those ice sheets. All ice sheets and glaciers start as snowfall. Those tiny flakes get compressed by the weight of more snow above, and eventually become dense masses of ice.
What we're seeing right now on the ice sheets and with glaciers is that they are shrinking in size. And as glaciers on land are shrinking overall, that contributes a little bit to sea level rise. And we are worried as we see warming over the ice sheets and increased melting over the ice sheets that they are going to start contributing much more to sea level rise.
2/3 of the fresh water on Earth is frozen in the world's ice fields. If that ice melts, seas will rise. If all of that ice were to melt, sea level would rise worldwide by 70 meters. No one expects all of that ice to melt anytime soon, but even the meter of sea level rise that many scientists predict in the next century could have dramatic consequences.
Even though the polar regions seem very far from a lot of people's day-to-day life, they are very important because they are the regions that cool our Earth, and as they change, they're going to cause larger changes throughout the rest of the globe.
A lot of people live in coastal areas, coastal places that have beaches. As sea level rises, then beaches begin to erode, and we begin to lose wetlands. A lot of different ecologically sensitive regions lie along the coastline, and as sea level rises, these get flooded, the ecosystems are forced to change. And so all this can have big consequences for people, and especially people who live near the coast. As the great ice sheets in Antarctica and Greenland begin to melt and break up due to global warming, we really might experience very rapid sea level rise, 3 or 4 times as fast as the rate that we see today. So predicting this rate out into the future is very tricky because we really don't know when the ice sheets might break up and how fast they will when they do. So predicting future sea level rise is one of the great scientific problems of the future.
Good morning, and thank you for having me here in Breckenridge. It is a great honor to get to come up here and talk to you a little bit about Operation Icebridge and how that video summarized it pretty well, but what's happening with our global ocean and how the ice sheets are affecting that. And I'll actually show you some of the actual research we're doing. I'm an observationalist, so that means I use satellites as well as ground measurements on the ground to really look at the ice sheets and see how they're changing. So I start out with this image. It's a pretty iconic image. This was shot in 1972 by the Apollo mission. It is known as the Blue Marble. And I show this, it started kind of one of the modern environmental movements. But what's very unique about this, and most people don't think about it, is that it's one of our first images from space of Antarctica. So Antarctica is actually in the sunlight, and we got to really see the shape of it, the sea ice around it. And this was just in 1972. It's not that long ago. So I say that because understanding the ice sheets, it's relatively new. They affect the globe, but we're still learning a lot. Why do the ice sheets matter? This is an animation of the thermohaline circulation. So these are our ocean currents. And what you'll see is one of the major pumps in the ocean is right off of Greenland. How the water that comes off of Greenland and the Arctic sea ice changes, it affects this pump, this whole global ocean pump. And the ocean waters come up to the polar regions to be cooled. So this pump starts off of Greenland. It circulates throughout the globe where this cold, dense water will sink, become the cold ocean currents. They come down, they start to circle Antarctica in the Antarctic circumpolar current. You'll see that one of the fastest changing places in the globe, the West Antarctic Peninsula, the Antarctic Peninsula that sticks out here, that sticks out into those ocean currents. That's part of the reason it's one of the fastest changing places. So the ice sheets are intimately connected to the globe, especially through the ocean. They're the areas that cool our Earth. Now, the second animation that I have did not come across, but I'll use this to show it. We saw it in that opening video. The other reason the polar regions are very important is because as the solar radiation comes in, it reflects off the poles. So we have the solar radiation coming in. If it's a nice white surface, it reflects back. When you ski this afternoon, make sure you put on your sunscreen. It's that same effect. As we lose sea ice, the ocean is darker, it absorbs that light. So I say this as well as the ice sheets become darker, they'll also start to absorb more of that sunlight to warm up. We can state it quite simply. We need our poles to stay cold. We need our poles to stay white. People always ask me, why do you study the cryosphere? So cryosphere is areas of snow and ice on Earth. Well, here's a picture of me circa 1982 in Eugene, Oregon. It didn't snow a lot there. But you can see I was out enjoying the snow. Snow is fun. I am honored to get to study snow and ice areas. I can't imagine anything that is more fun to do. You'll also see in Snowmageddon storm, if you remember, in Washington, D.C., in 2010, here's my son. He's out plowing out the neighborhood. He's decided to take his cozy coop and turn it into a snowplow. Snow and ice are always fascinating. fascinating regions to study. And I think all of us can remember back to playing in the snow, as you will do this afternoon, and understand why having snow and ice on Earth is a pretty important thing. I start out all my talks with just some background information, make sure that we're all in sort of common ground, common terminology. The ice sheets. So we have Greenland and Antarctica. So these are our two major ice sheets on Earth. And Antarctica is much larger. It's about 1.5 times the size of the lower 48. Greenland's smaller. It's about the size of Alaska and the Pacific Northwest. Again, North Pole, South Pole. What's going on right now with the cryosphere and contributions to sea level rise? So this is really interesting, these charts. Now look at the red line. The red line is glaciers. Right now, glaciers, so the Alaskan glaciers, the Himalayas, these are the areas that are contributing the most to sea level rise currently. There's not a lot of ice in the glaciers compared to the ice sheets. And as you see that line, it's going out, but it's flattening. And it's going to start to flatten out. And what you'll notice is that the green line is Greenland, the blue line is Antarctica. These ice sheets are starting to increase their contributions to sea level rise. Question?
This does not include the contribution from expansion of the ocean, right?
This does not. So this is not including the expansion of the ocean. So sea level rise is about 3 millimeters right now. And this is just what is coming per year. This is just what's coming from the ice sheets. So not expansion. And they're about equal, I think. But the important thing to note is really, again, that we're having accelerated sea level rise and mass loss coming from the ice sheets. And we expect that these curves will continue to go up at that rate. And quite quickly, Greenland, in the next few decades, will be outpacing the glaciers in contributing to sea level rise. And I'll start to show you some of the measurements that we have leading to that. As the video pointed out, 1 meter of sea level rise in the next 100 years, that's a pretty probably middle of the road number right now. This is what it would look like. The areas in red would be inundated with water. You can see globally, Indonesia, Micronesia suffer more than other regions. The east coast of the United States and Florida suffer more than the west coast. And it's not quite equitably distributed. You'll see in the IPCC reports that the sea level rise estimates are a little less than a meter. A lot of the observationalist papers that are coming out in the literature right now are a little higher, and 1 meter is probably a pretty good middle of the road number. Few definitions as we move to the ice sheets. So this is a schematic of an ice sheet. We have sea ice, which again, frozen water on the ocean. It does not affect sea level rise. It's on the order of about 10 feet. We have ice shelves. This is where the ice flows under its own weight, goes out and floats on the water. They're about 1,000 feet in thickness, and then we have the actual ice sheet. And the ice sheet itself, are miles thick. There's some important points here. I'm going to point out where the land, water, and ice come together. We call this the grounding line. This is a very important point. We want to understand how the ice is flowing. Once it flows across that point, it is actually affecting sea level rise, as well as interacting with the warm waters of the ocean. Ice doesn't tend to like water. That'll be a theme throughout this. Usually when ice and water interact, the water is going to win. What we're really trying to monitor and measure is what's called ice sheet mass balance. Snow can accumulate, so we have snow coming in mainly as precipitation, and we have ice that flows out. We need to know what comes in minus what goes out, and we'll understand the mass balance. We can lose ice through that natural flow where it flows under its own weight and flows out to the ocean. Can also melt, run off as water, sublimate to the atmosphere. So we mainly have precipitation coming in, and then these different ways that we lose or ablate the snow, mainly, again, flow into the ocean or melt. So when I talk about that ice flow, question?
Yes, we have a question coming in from the live stream, actually, and this is Cheryl Nelson with Storm Center. And the question is, how do we separate the impact from anthropogenic and insulation?
So what I'll start to talk about now is these warming temperatures over the ice sheet and how that's causing melt. And we do know, and it'll be actually towards the very end of the talk, I'll show you about CO2 temperature rises and how throughout geologic history that has affected. So what we're pretty sure of right now, what we know, is that CO2 levels have risen and the temperatures over the ice sheet are rising. So on to ice dynamics. Traditionally, until just about 5 years ago, I'll talk about a major change that's happened in the Greenland ice sheet. Traditionally, we think of most of the mass loss coming from ice sheets through ice dynamics. We've actually been able to measure the flow of ice. That's what it's showing here. Ice flows under its own weight. It creates rivers and streams. These images show in the red colors, the blue to red colors, faster flowing ice as it flows out towards the ocean. And then slower ice is in the interior of the ice sheet. This is called ice dynamics. Here's a quick animation of what this actually looks like, the ice flowing towards the sea. This is the general mass loss mechanism that we think of, and we can measure it quite well with satellites, and we can measure the changes in it. Most of it is speeding up. A few areas have slowed down, but overall, it's mainly speeding up, and ice has been steadily moving towards the ocean. So this is in Antarctica. The longer the arrows, the faster it's moving. You see it moves faster towards the coast and slower inland. So we've been able to monitor this for a long time, and we have a pretty good idea of how the ice flows. And again, we'll talk about that coming up, but just so you understand when I talk about ice dynamics, what we're talking about. We can observe the ice sheets from 3 different methods. And what I'm showing in this slide is satellite research, air-based research, and ground-based research. And on the charts of Antarctica, to your right-hand side, you'll see that the red areas are the areas that we can cover, that we can monitor in one season with either a satellite, air-based research, or ground research. You probably can't see, but there's a very small, here, red triangle of where ground-based research can occur. Now, these scale from top to bottom, from bottom to top in price as well. But if we're going to monitor the mass balance, what's going on with the whole ice sheet, we really need to be at that satellite level. And if we're going to go down to the ground-based research level and just study a very small piece, we should be doing that to either validate the satellites or understand a process, because we're not going to get as much information at that level. So in 2002, NASA launched the first satellite that was directly related to monitoring the ice sheets. It was called ICESat. It was a laser altimeter, so just like a laser pointer can point out and hit a wall, the laser pulse goes out, it hits a wall, it comes back, and it tells you the distance between the spacecraft and whatever surface it's hitting. What we learned from the laser altimetry, we got the shape of the Greenland or of the Antarctic ice sheet and high-resolution DEMs like we hadn't had before. And we also, if you take the height change over time, we started to see areas of thinning. So in Greenland, in the blue areas around the edge, those were areas where the ice was thinning. In red, areas where ice was getting thicker. And there was a very good summary paper of this by Pritchard et al. In 2009, And what you see is the areas in red, those are areas that were rapidly changing. In West Antarctica, you see a lot of red along what we call the Amundsen Sea coast. Those are glaciers that have been receding, and recent reports are showing that those glaciers have sort of reached the path of no return. They're grounded below the sea. That grounding line that I talked about is receding back, and we're going to have significant sea level change from those regions, but over the longer term, at hundreds to thousands of year time frame.
Joe Murgo from WTAJ. When you're talking about the ice height change, is it taking into account the mass of ice or also some ground shift from change of weight? That's there too, isn't it?
Yes. So this, and I need to think about this in this particular paper. In this particular paper, they are looking at DHDT. They will be taking out the motion of ground motion. The other thing that is most important in some of these measurements is actually how the ice compacts on itself. Okay? So right now, we'll use this as DHDT, and we're not going to talk a lot about mass yet. So what this is saying is this is pointing out the regions where we see a surface lowering, and it turns out in a lot of those areas we'll end up seeing large mass change here. But these are just areas of thinning. And what ICESat really did is it was able to take these large masses of area and show us the regions that are really important. And a lot of those regions there are in red. And I say that because in 2008, I should say I'm at the National Snow and Ice. I work at the National Snow and Ice Data Center now, but before that I worked at NASA for 6 years. Right as I arrived at NASA in 2008, ICESat started to fail. They knew that the laser was going to fail. So here was ICESat, our first polar mission. And they knew it was going to fail, but we knew that the ice sheets were also changing rapidly, and that in the next decade, they would be changing very rapidly. So they started Operation Icebridge. They said, what can we do? We don't have a next satellite built, but we can take that LiDAR that's on ICESat, we can put it on an aircraft. Well, we're not just going to put that on an aircraft. We could also put some lasers and radars. So the green lines are showing laser altimetry, but, you know, a plane is much bigger than a satellite, so we can add any other instruments that we want to it. And we also added radars that peer into the ice. Operation Icebridge is bridging the gap until ICESat-2 launches. ICESat-2 is scheduled to launch in November of 2017. So Icebridge, which started in 2009, is going to end up being almost a decade-long mission. Now, again, we don't get the coverage, but for the lack of coverage that we get with Icebridge, we get many more instruments. This is just a schematic of our P3 aircraft outfitted with all the different instruments. There's actually 4 radars on board. You see the little red patch. Those are some of the radar antennas, as well as the antennas that are hanging out on the wings. It's one of the most sophisticated depth-sounding radars in the world, able to penetrate down to the depths of the ice sheet and measure what the bed is doing. We have photogrammetry system on board, magnetometers, temperatures that measure the skin temperature as we fly over, and then again the primary instrument, the laser, to monitor those surface changes as they go up and down. Let's see if this one will work. Oh, well, that is unfortunate. Let me try one more time, because I believe this one should have started on its own. Well, what this animation was going to show, let's hope there's no more like that. Don't worry, I have a thing. The animation actually showed the aircraft flying over, and it showed a green line that kept pinging off the surface. And that green line that pings off the surface, it shows that LiDAR's they don't penetrate into the snow. They measure just that surface of the snow, so how the surface is going up and down. The radar, which we're showing here in red and blue, we actually have, again, I said 4 radars on board. The 4 radars look to different depths into the ice sheet. One about 1 meter, 10 meters, 100 meters, and then thousands of meters down to the bed. So it gives us this 3-dimensional view. And those near surface radars, the radars that see in that 10 to 100 meter range, those are things that we had never had on an aircraft before. I'll talk about that coming up here as well. But it was the first time that we really got a peer at the near surface of the ice sheet, and we've learned a lot from that. So again, as the aircraft flies over, it monitors the surface of the ice sheet, it monitors where the bed is, it can monitor the thickness of the ice shelves, as well as the temperature. And the gravimeters and magnetometers on board, they're quite interesting. They've been able to measure where the bedrock is and capture what the fjord cavities, so that water that's underneath the ice shelves and glaciers, what that actually looks like. Again, IceBridge has gone beyond what the satellites could show us, giving us this 3-dimensional view. Operation IceBridge is the largest airborne survey ever flown. This is just coverage. It's not updated. We fly every year. We fly Greenland from March to about mid-May. We've just initiated in the past few years, so that's measuring the ice sheet and the sea ice at its highest extent. We then measure, we've just started in Greenland what we call a fall campaign. We measure again in late July, August. And then in November, December, we fly over Antarctica. So you can see the plane is very busy. The instrument operators are very busy. The flight lines, because it is airborne as opposed to satellite, we get to fly regions that are important. I actually will leave right after my presentation to fly out to Washington, D.C., where we will be planning the flight lines for the Greenland season, which is coming up here in March. We have some baseline missions that we fly all the time, as well as we have the flexibility of when regions are changing rapidly, we can redirect some of the aircraft resources to really study those regions. Again, we fly over both the sea ice and the ice sheets. Here's just a little schematic here again of those flight lines in Antarctica. You see that the Amundsen Sea coast, you see they're called Pine Island and Thwaites glaciers. The regions where we had seen those large red dots from the altimetry measurements, we've monitored those quite a bit. And like I said, there's just been some recent studies showing that those glaciers have come off of their grounding line. They're below sea level, and over time, these will eventually recede back. And those are the regions where we'll probably see most of the sea level rise that comes from Antarctica. You can also in this see how the flight lines do extend in the Weddell Sea out over the sea ice. All right. This one better work. So this is what it looks like on the ground. You're going to see, you see at the very bottom there just the tip of the P3 as it taxis out of Thule Air Force Base in northern Greenland. These are some of the early flights. We'll take off. And the first flight that we'll see will be over sea ice. You're flying out of the fjord there. So here we see over sea ice, you see the cracks and the leads in the sea ice as it moves around. We're able to monitor how much snow is on top of the sea ice, as well as the thickness of the sea ice, combination with the radar and LiDAR. Here we're flying, I believe this is over the Geikie Plateau in Greenland. We can fly down the glacier valleys. We fly quite close, monitoring how the ice is changing. Here's the downward looking video camera. You'll see as they go over this peak how closely we fly. We fly about 500 meters, 1,500 feet off the deck to monitor these. So what contributions has Operation Icebridge made? Well, it's actually made a lot. And I'm just going to highlight a few that I think are kind of important. So Jakobshavn Glacier is on the western Greenland coast. It's also one of the fastest moving glaciers in the world. And when we're talking about the radars that see all the way to the bed of the glacier is very important. If you think of putty or honey flowing over a bumpy surface, you need to understand the bumps to understand how fast it's going to flow. It's the same with ice. And the better we understand the bumps that it's flowing over, the better we can understand what is going to happen with that particular glacier. So what's on the left is what the previous bed map looked like. So again, take the ice off the ice sheet. We're looking at the very bottom, so the ground where the ice and the ground interact. And it didn't see this trough. And in Jakobshavn, there's this trough. And the radars on the ice bridge, so on the right-hand side, you see that blue area. Blue is low. That's a trough. And we were able to really update the resolution of the bed map in this area. Well, what did that mean? The modelers have been asking for this. When we talk about sea level rise, sea level predictions, that's coming from the models. So our observations better be informing the models. So first we had observations of surface velocity. That's on the left. In the middle, we see what the models produced with that previous bed. And then with the improved bed map, you can see on the far right that the right and the left are starting to look more alike, and that we're able to improve those models with that new bed map. Now again, we're improving the bed maps over both Greenland and Antarctica, and that is a major focus of the mission. One of the other very important reports that came out, this was by Ellen Enderlin in 2014, and I'll try not to show too many graphs, but this is an important one. First, what you see in gray is just the mass loss from Greenland. So Greenland is losing mass throughout time. Remember, ISAT ended in 2009, and we knew that the ice sheets were changing, particularly Greenland. So we're looking at Greenland here, and that blue line, it's declining, but rather steady. That's ice dynamics. That's ice flow. When I talked about how most of the way we think about mass loss coming from the ice sheets is that ice slowly flowing and moving out. Well, what happened in about 2007, some reports put it to 2009, you see the red line and the blue line cross. The red line is what we call surface mass balance. That's what's happening on the surface of the ice sheet. It's dominated by melt. So we went from an ice sheet that was mainly losing its mass through ice flow to one that's losing its mass from atmospheric warming at the surface and water flowing off. This was punctuated in 2012, that we were getting more melt over the Greenland ice sheet by an extreme melt event. This is in July of 2012. What the red is showing on July 8th on the left-hand side is, and this is actually a pretty typical melt. The red is areas that were experiencing melt, and then as we went into 2012, on July 12th, the entire ice sheet experienced some melt at the surface. That doesn't mean that it all ran off. Some of it just percolated down and refroze. But this was just a highlight event that really punctuated that Greenland was experiencing more melt and losing more mass through water and shedding of water. Now, you can actually look at the July 8th. What's maybe more important about this is that we've been monitoring this melt extent since the late 1970s. And it has steadily been increasing. So that's sort of showing a mean state change. More area of the ice sheet is experiencing melt on a year-to-year basis. So even more important that the melt extent we had an extreme melt event, is that over time and throughout the years, the melt area on Greenland is increasing and increasing steadily at a constant rate. This is a satellite image, I believe taken exactly on July 12th. And it shows you what Greenland looked like in the melt area. When I first introduced the polar regions is important, saying we wanted them to stay cold and white. What you'll see on the very periphery, especially on the western edge of Greenland, is that you have this dark band. That's where we've melted off all the snow, the dust, and the fancy word for it is cryoconite, but basically dust is starting to concentrate, makes it a relatively dark surface until the winter snow falls on it again. And then above that, just up from that dark band, you'll see a blue band. That's the area where all these superglacial lakes are forming, rivers are forming, and on the west coast, those are evacuating that meltwater quite quickly. So this is sort of the emerging picture of what a melting, surface melting Greenland is looking like. Well, what did that melt mean? Those drainage features, that light blue area you were seeing on the edge, they were evacuating the water from the ice sheet quite quickly. They were quite efficient. And the meltwater came down. This is outside the town of Kangerlussuaq, Greenland. The rivers swole quite quickly. It knocked they were worried about the bridge, knocked one of the caterpillars off, and it eventually knocked out the bridge there. So it's real effects. This is a image from the New York Times. Researchers Larry Smith, they study how efficient, especially on the West Coast, these networks are at evacuating the water once it melts. And I bring this up because, you know, this is the picture, we were looking at that picture of ice flow. Well, this is the picture of how most of the mass now is leaving the Greenland ice sheet. It's these river systems. And even though the lakes, and I'll talk about the lakes, are important and they store water, these rivers are really evacuating this meltwater off of Greenland. And this is particularly on the west coast. I'll also talk about how that's a little different on the east coast. But again, Greenland went under a fundamental change during the ice bridge era while we were monitoring it, where it went from an ice sheet that was losing mass from ice to losing mass mainly from surface meltwater. And that's a big change. And Antarctica is still losing most of its mass from that ice motion. So now we have to actually talk about them like they're different ice sheets. So I've actually talked about a lot of the ways we're losing mass from the ice sheet. Well, that's actually not what I study. What I study and have always studied is that side that might buffer sea level rise a little bit, and that's how much snow is falling. And the model projections, this is a bit outdated, but it still it still rings true. In 2007, the IPCC put out a report, and the models showed, well, with warming climate, it's amplified in the Arctic, warmer air, we're going to have more precipitation. And if we put precipitation on those high, dry, cold areas of the ice sheets, maybe we could sink a little bit of precipitation and mitigate sea level rise. And even though they said that this could happen, this increased storage of ice, it had never been observed to date. And so what I try and study is precipitation. Now, how we study precipitation on the ice sheet, we have snow and firn. When snow reaches its first birthday, it becomes firn. Snow falls, and it builds up layers, just like tree rings, over the ice sheet. It compacts under its own weight down to ice, but you get snow every year, and you build up these layers. This is in the most simplistic case. Now, we can measure precipitation with ice cores. In Dr. Brown's introduction, you saw a great video, and Dr. Jim McConnell was highlighted in that. He's taken many, many ice cores over the Greenland ice sheet and has shown us a lot about what precipitation, how precipitation has changed, and what's going on with Greenland ice sheet from ice cores. So ice cores, however, are just a single point measurement. And ideally, as we have, I pointed out in Icebridge, these radar systems, we'd love to be able to measure precipitation or accumulation over larger areas using those radars. And I had been planning a field traverse. It was called the SEAT Traverse, Satellite Era Accumulation. This was before, remember, going to Antarctica, we're going to go to Antarctica now. Going to Antarctica takes a lot of time and planning. So we were actually planning to take these radars out, these near-surface radars, which now fly on Icebridge. We were planning to take them in the field for the first time to really monitor how they would do. And we're going to take them to West Antarctica because, like I said, if we're going to do something on the ground, it better be a really important place so that we're getting the information on processes that we need or validating the satellites that we need to take this back up to the satellite region. And in West Antarctica, it turns out there's like a 4-fold change in accumulation over a few hundred kilometers. So we were going to take these radars out, see if we could measure that accumulation over that region. To get to West Antarctica, you take LC-130, run by the Air National Guard. This is our team. We've left McMurdo and gone out. This is actually at Waste Divide Camp where they were drilling a deep ice core, and we were going to go out from there to drill our own little ice cores. Here's just a map zoomed in again on West Antarctica. In the first year, in 2010 to 2011, we did the red line. We traversed again across that divide. And then in the 2011-12 season, we did the blue line. You know, about 400 kilometers each year, and we drilled ice cores along the way, and then again tied those radar measurements to them, and I'll show you how we did this. This is on the bottom what the traverse looks like. We use snowmobiles and camp out, and then in the very back there we have the radar sleds. Here's again what those radars looked like. Was one of the first times we were taking them out into the field, and simultaneously they were loading them on board the Operation Icebridge. First, I'll talk about measuring accumulation from ice cores. So here's our ice core drill. This is a small drill. It's only going to go down about 20 meters. They're drilling down. You'll see this is a mechanical drill. It cuts through. It has little cutters. It cuts through the ice, brings out a core. This is Randy and Jessica taking that out. We're going to push the core out onto a table for core processing. And that core will eventually get taken back to the lab. Here this just is in pictures. Again, we dig down, we send the ice core drill down. We measure a few things in the field. We measure the length of the core, the density of the core, the electrical conductivity, which is the dust, kind of the dustiness or the chemicals in the core. And then that core will go back to the lab, put it in a bag, put it in a tube, put it in the white ice core box. It gets shipped back, where they can actually do the isotopic analysis, which will date that core and show us how much accumulation was in each layer.
Are you working in constant daylight? What's the temperature?
Yes, so we are working in constant daylight here. So this is going to be December of 2011. And the temperature is probably about -30. It's not particularly cold because it wasn't super windy. Usually in this area it's the wind that makes it cold. And when the sun's out, it's quite nice. I always ask on this how you know, Jim does not get an answer, how you know which is the top of the ice core. Can anybody tell?
No, I can't tell.
The arrows point to the top. It's very important to keep these in order. Yeah.
What's your elevation at this location?
Oh, I should know that, and I do not have it off the top of my head. We're at 3,000 meters, something like this.
So roughly 10,000 feet, so you're high.
Yeah.
Was that minus 30 Celsius or Fahrenheit?
Celsius. Actually, and they are close. They'll cross at negative 40, so that's always the clear bet, is just say negative 40. Negative 30 Celsius, and I will say if I'm talking about numbers above freezing, I'm probably talking about in Fahrenheit. If I'm talking about them below freezing, in Celsius. You asked about the cold too. You see a little trick of the trade. The coldest area is actually where your feet are contacting the snow, where the cold is being conducted through your boots. So we're standing on these little green thermarest chairs that we use later to eat our meals on, but it gives a little extra insulation for your feet. Here's just a picture looking down the borehole. You're looking again back in time where the ice core came out of. Now, ice cores, again, they're just point locations, and if you go out here and ski today, and if you were to take a snow measurement at many different places, you'll see that actually it's quite different. There'll be different levels of snow depending on the trees that you're in, different things like that. So we really want to understand how these point measurements are connected through space. So now we're going to take the radar and we're going to connect those ice cores to see if we can get that same accumulation rate from the ice cores. Here I'm going to show you the radar, an animation of that radar data. Again, think of this as like tree rings. So this is the radar. We're peering down into the ice sheet. We're going along our traverse. We're on the low accumulation side of the divide. The layers are pretty jumbled. At 10-3, we start to cross the divide. We're coming to the high accumulation side of the divide. You'll start to see those layers are more pronounced. You can start to pick them out a little bit more, count them a bit more like tree rings. And then, again, as we go back across the divide onto the low accumulation side of the divide, we're going to have more difficulty really distinguishing what those layers are. Now, what the radar is responding to, radars respond to changes in density. And so what this really is, these radar reflections here, is really a response to the density changes in the ice sheet. And those density changes are seasonal. What we found, now we're going to go to the high accumulation side. This is a zoom in of one of those radar data. We have at 0 is the surface, so the gray below is atmosphere. We go into the surface of the ice sheet, and again, we see that snow, we see the bumps and that layering from year to year to year. We can take our ice core measurements. We know how they were dated. We can connect those layers across, and we can actually start to count accumulation over space and extrapolate it from those ice cores. Now, the very important thing about these radars that I haven't said yet is that they measure things that are about 4 centimeter resolution. So these are higher resolution radars than we've ever had before. And it's the first time we're actually able to resolve this annual layering. And what we saw is that we actually don't need those ice cores. What we can do is just start to count back in time from the surface and get accumulation directly from the radars. And again, the radars, you know, we spent 4 weeks doing the field campaign the first year, 6 weeks the second, including all the travel time there. The airplane with the same radars, we're over to overfly that in a few hours without cold fingers. And the radar data on the ground and in the air was very similar. So what we learned from that is that we can trust the airborne radar data and use that to look at accumulation. What we did with this data for Antarctica, we haven't processed all the data yet for Antarctica, but we've made this map of blue and red areas. So the red are areas where the radars probably won't work to understand accumulation, and the blue are where the accumulation rates are high enough that we actually can use the radar systems to monitor and determine accumulation rates. In the red areas, the fancy word is post-depositional processes are occurring that jumble those layers. And what that basically means is the amount of snowfall that comes in is in proportion to the amount that's being blown around or sublimated away. So those nice tree ring layers, they're all jumbled. and we can't make sense of them. So I'm going to hop over to Greenland because I said we hadn't processed all the data yet for Antarctica. It's a bigger area. It's a bit more complicated. Greenland has higher accumulation than Antarctica, and we were able to produce the maps from the ice bridge flights of accumulation. So this is the amount of snow that falls and is left after any sublimation or melt throughout the year that is left on Greenland. And what we've been able to do with this, on the right-hand side, you see modeled accumulation. Before this, besides the ice cores as our measurement of accumulation, this is our next best measurement of accumulation. And beyond that, we were modeling accumulation. And we've actually been able to compare these to both regional and global climate models. And what we see is that the models are actually doing a relatively good job. On different years, they do worse, and they generally have the most trouble in Southeast Greenland. That's the area where it's blue down there. Southeast Greenland has the highest accumulation the highest accumulation area in Greenland. That's because the Icelandic low sits over there, pumps all the storms in. And that the models, it also has a lot of topography, and the models, especially the higher resolution models, seem to have a little bit of trouble in that region. But overall, we were quite surprised at how well the models are doing and give us quite a bit of confidence in our projections. So what I told you I study and what I want to study is accumulation. But as I've been looking at my accumulation signals, especially in Greenland, I start seeing these very strange things. So again, here's these radar echograms. You see the snow surface. You'll see a second little layer there. That's the annual snow layer. And then you see this bright black thing. And we actually, in 2011, I was on the plane when we were flying over these features, and one of the radar operators said, "Hey, Laura, come over and look at this. What is this?" And I said, "Oh, we're flying over the regions of the ice sheet where superglacial lakes form in the summer, and that's just the refrozen lake. And the refrozen lake, we're getting a reflection from the surface." Well, again, these are the 4 different radar systems. They look at all the different depths throughout the ice sheet. So you see the one in the bottom right corner, you see the actual bed of the ice sheet there. Well, all the radars were responding to it. So if it was just a reflection of ice, all of the radars would not respond to it. What all radars respond to, just like you can microwave your food and it gets warm, that's because in the microwave part of the spectrum, which is where the radars operate, water is absorbed. And so those waves are absorbed. The water absorbs those waves. And so when these features were being seen in all the different radars, we knew that it must be water. And that, in fact, these lakes were not completely freezing. We thought they were, but they hadn't been. So we have a layer of snow, we have lake ice, and we have water. Now, we generally fly in April, around April timeframe. So we have the snow on top of the ice sheet. So most of these lakes, these buried lakes, which we call them, we couldn't actually see surface expressions of. But in one, we did have a surface expression. And what you see here on the right-hand side is sort of your normal ice. Then you'll see a bright blue band. That's actually where the lake edge was, the beach, if you would. And it froze. It wasn't very thick. And then over here on the left-hand side, you could ice skate on that. You could drill a little hole through it and go ice fishing because there's water underneath. You probably won't have much luck. But this was our first image where you can see the clearness on the left hand side that we were actually seeing this water that had been stored in the ice sheet all winter. And we saw that, there were quite a few of these on the west coast and also in northeast Greenland. So we're getting this picture of Greenland that's really evolving. It's an ice sheet with a lot of water in it, and that water is persisting throughout the winter season, and that means that it's warming the ice sheet. It's warming the ice sheet internally. Now these lakes, it's actually not a lot of water. In the same time we were discovering these lakes, we had some colleagues, and they were traversing down into southeast Greenland. I mentioned before, southeast Greenland is one of the areas of highest accumulation in Greenland. And because it's such a high accumulation area, yep.
I'm just wondering if you have any idea as to how old those buried lakes or how new those buried lakes are.
Yes. So, you know, I don't think that they are, well, it depends. Here's what we've discovered about the buried lakes. When I showed you the streams, those lakes tend to bury when they are not connected with streams to other lakes. So there are areas where the ice sheet is starting to melt. It's ponding, but it's not yet connected to the evacuation system, right? To the ocean, to evacuate it to the ocean. So they're probably only persisting for a few years until that pond, it's actually an evolutionary feature, until that pond can make connections to other lakes and get into the river network system that will evacuate that water eventually. We do see that they persist for multiple years, and that some years they come to the surface and remelt, and other years they stay buried all year. So it's really on this sort of edge where the lakes are not yet connected, and they are, but we're starting to get meltwater to produce the lakes. So again, they're probably in an evolutionary feature that is, once it's connected, will start to die out more, and that water will go to the ocean quicker. So southeast Greenland, there hadn't been a lot of ice cores taken there. There hadn't been a lot of ice cores taken there because it is a nasty, nasty place to work. If you are a Twilight fan, it's like the Forks of Greenland. But we knew it's really important for the models because we needed to get accumulation right there, or it can change the whole surface mass balance of the ice sheet because it is such a high accumulation area. So a group was taking ice cores, and they were traversing down towards that blue area. And as they were traversing towards that blue area, they'd taken 2 ice cores. That was just fine. They drilled down, and they went to drill their 3rd ice core. And the driller was drilling down, and they pull up the ice core, and the drill, these are expensive pieces of equipment, was dripping water. The driller was not excited about that because these drills are not supposed to be in water. And he said, "What's going on?" Well, they were dragging a radar with them again. Here's the radar echogram. You see the surface, you see those nice layers, and again, you'll see this cross-cutting bumpy area. Well, that was water. The first act A2, that first white line there, those are where the ice cores, they drilled down and they hit water. And they did this twice before the driller said, "That's it, I'm done. We can't drill in these conditions." And they called Icebridge. They knew we were flying these near-surface radars that would also be monitoring where this water layer was. And what we found when we went back through all of the radar data, again, looking at this near surface, we hadn't done this before, Operation Icebridge, that all of these blue, red, and green dots, these are all regions where we were storing water at depth in what we call an aquifer in southeast Greenland. It was just discovered again in 2011. It was a pretty large area. You see most of the depths, the actual colors on the right-hand side. Those are zoom-ins to show you the depth below the surface. On average, it's about 10 meters below the surface, all the way up from 5 down to 30 meters. And what this is it's meltwater that's percolated down and stored in the ice sheet. Well, we just discovered this, so I was actually part of the team that got together to take a different drill back in and figure out what this was, where the water was, how deep it was, how thick it was. We really didn't know anything about it. We had to take a different drill. What I'm showing on the right-hand side there is a thermoelectric drill. Instead of mechanically drilling, this heats down into the ice so we can heat down through. And you see it's coming up, it's dripping out water. We're collecting it in a bottle there. We saw some really interesting things here about this snow above where this aquifer sat. This is just a piece of that ice core. And everywhere where you see the light coming through quite well, those are ice lenses. And we call this piping. So it showed that the surface meltwater was able to pipe down through the snow quite rapidly. It became insulated. This area would then snow on top of it, and that water could percolate down fast enough, become insulated, and then store year-round as water as opposed to ice. And then that also, again, is warming the ice sheet. When you'd pick up these cores, if you remember from the 80s, these sort of oil and water things that you could tilt back and forward, you could pick up the core, and you see there's a bunch of water towards the left-hand side here, and you could tilt it back and forward and watch the water within this ice percolate back and forward. We took the temperature. Again, what water does to the ice is it warms it up. More water you have, you know, it's got to stay at 0 degrees. It warms up the ice. When it refreezes, actually, it releases latent heat. It warms up the ice even more. Now, remember, the models would be predicting that this amount of, you know, at this depth, that it's probably about, you know, negative 20 degrees on the ice sheet. And what we found is there's water there, and the ice sheet is in fact 0. So this is kind of on the left a joke of how we take the temperature, but we're putting in this thermistor string that monitors the temperatures here year-round.
So what you're saying is the actual depth temperature is much different than we originally thought of the ice sheet.
The temperatures of the ice are much warmer than we would have originally thought because of this large storage of water.
And is there ever a tipping point with the water built out underneath that you're going to expect is there a potential that one day is going to be a big?
Yep. So I'll talk about that in the next few slides. But I mean, water, you know, it can build up. I'll show you that we see that it is evacuating at kind of a constant rate. But it's also growing inland. So, you know, it can't stay there forever. It's probably buffering right now. This is buffering. Some of the water that should go out to sea level rise is being buffered. And the real question that we're trying to answer is how long will it buffer? Because it's water. It's got to come out sometime. And I'll show you. We've taken water hydrologists with us. So now glaciologists, we all have our favorite hydrologists to take with us into the field. And we're starting to measure how this water can flow within the aquifer.
Jim Gandy at WLTX in Columbia, South Carolina. I got a question for you. You say that the water in that ice is warming the ice sheet. Is there any evidence that in turn is having an impact on the air temperature above it?
No, this would actually be relatively insulated from the air temperature above it. So this is more the air. This is the air warming the ice sheet. Then that water percolates down, and it's insulated. And the whole reason it can stay as water is because there's enough snow on top of it to insulate it from that cold air. So that would work in both ways. It's being insulated from the atmosphere in that way. So. And this is just kind of fun. So we're going to stick a borehole video camera down. We're not actually taking science measurements with this. This is the same instrument that they would snake out your toilet with. It's called a sea snake. We're just looking at what did this look like. We just drilled into it for the first time. What did it look like? And I'm going to show you this video here. It'll start automatically, but you'll see bubbles coming up. Now we're 11 meters down. These chips there are actually the chips from drilling sitting on the ice sheet, and we're going to go down. Again, we're 11 meters below the surface of the ice sheet. You'll start to see this water and bubbles. So this is hidden beneath the ice sheet. Again, the radars from Operation Icebridge were really able to show this. And as you get deeper down, there's not as many bubbles because towards the top of the aquifer, you have both water airspace within the ice, and then as that water percolates down due to gravity, there's less airspace. Yeah.
Dave Jones with Storm Center. I'm just wondering, when you see this, you know, everybody has insights that are right there, and you as a researcher or anybody else, is this like a moment where you say, oh no, or this is bad, this is good, or we just need to learn more?
So, you know, I say this could be both good and bad, actually, because this is buffering some sea level rise, right? And there have been papers written that the Greenland ice sheet could help buffer sea level rise, at least temporarily, by storing some of this water. What we're seeing, and a paper just came out 2 weeks ago, is that a lot of times it's actually not buffering, it's not refreezing, or it's refreezing so much that it creates ice lens that makes it more efficient to have this water run off. But, you know, did it scare me? What it did is it made me think that the ice sheets, at least in Greenland, the ice sheet is behaving a lot more similarly to a mountain glacier. Mountain glaciers have this water storage in them, and that we should actually, where we had been thinking about the ice sheets as very different, that we should be pulling a lot from that mountain literature on how meltwater is percolating through mountain glaciers to learn more about Greenland. Now, for the scary side, I've given you all three answers, so that's not great. The other thing on the scary side is that if this water were to release, now granted it needs to build up for a long time, so this isn't anything that's going to happen quickly, but if it were to build up and release catastrophically, right, maybe one end member, you're releasing this water right into, when I talked about that thermohaline pump, you're releasing a lot of cold fresh water right into the ocean where you do not want to be releasing a lot of cold fresh water. Time will tell. This is ongoing research, and we're just really learning about how it's draining and how quickly it can go. Yep.
Amaze me with the bubbles. I have to ask this: is there any life down there?
You know, we have not taken samples for that yet.
I'm very curious.
You have to say, I would not be surprised. There's all sorts of extremophiles. This is a pretty desolate place, but I'm sure there could be microbes.
Yeah,
Yep.
The answer is yes. Yeah. Almost everywhere we look, we found the bacteria virus. You know, we're not talking about big things. Yeah. Microbial. Yeah.
Yeah.
Things in but they're all over.
Technically, we're adding it to it too, aren't we, by drilling?
Probably.
Yes.
Unless they sterilize. Right.
We have been, and that's been a big thing, right? We're the first people to kind of drill into this, and you don't want to be pouring, for instance, if ice core drills get stuck, sometimes they'll pour ethyl alcohol on them or something, and we did try keep clean practices. We didn't completely, sterilize the drill, but yeah. So we estimated it from our first drilling. We've gone back a few times now. From our first drilling, there's probably about 0.4 millimeters of sea level rise. Right, so that's a little less than a sixth of yearly sea level rise. So it's not a huge amount, but it's also not an insignificant amount. And here I'm actually going to show you. We've learned that this is a very dynamic feature. From the Ice Bridge radar. So here's the Ice Bridge radar profiles. Again, we're looking at the gray, the radar profiles from 2011, 12, and 13. And on the right-hand side, you're going to see this double bump. And that double bump was there in 2011, 2012, and in 2013, it's not there. And you'll also see on the right-hand side, there's some crevasses. And you probably can't see it from where you are, but the radar shows you where the crevasses are. And we see that the lower end of that aquifer, it's draining into the crevasses. And, over this, we have a 4-year time period to look at, but that it is drained. But we also see as we go inland, so as we go towards the zero distance mark, towards the left-hand side here, that water's filling inland, and we're seeing more water, and it's moving inland. Now that water, it'll take a long time to flow down and actually get to the crevasses where it can get out. And that's why when you talk about a catastrophic event, it's kind of hard to get a catastrophic event because you have all this ice lattice holding that water back, and it has to flow through it. Well, like I said, we all have our favorite all the glaciologists have our favorite hydrologists now. So we took Kip Solomon and Olivia Miller from the University of Utah, and let me go back and see if I can get this. And they took their piezometer down. Kip's used to working on aquifers around the world, on groundwater, and they put the piezometer down, and here he's pumping water out for some of the first water samples that we're going to take. These water samples are both being dated, and the piezometer tells us about the hydrologic head, or how the water can flow. And so here we're pumping water out of the ice sheet. Let's see if I can get this second one to start. There we go. And again, it's just a manual pump, so he's moving it up and down within this packer system in the piezometer that's isolating the water at the different levels. And they measure this for tritium dating to tell the age of the water. And we've just gotten a few of those dates back, not enough to probably talk about and make sense of. It takes a little while to get all those measurements, but that's what we're learning more. Now, I mentioned that southeast Greenland is the forks of the area, and so here we're actually, these are the typical storms that we get hit with. These are actually storms in Antarctica, but they're very windy. Well, when we were taking our first measurements, water measurements, we ended up getting our first snowstorm to really understand how, in the previous years we'd had pretty good weather. We'd lucked out a lot, but we started to figure out how much snow can actually fall in this region. We got 2 back-to-back storms. This image is taken from this video is taken from the first one. You see our tents there. And I've just walked out to the latrine. This is on a path that's actually been dug out. And this is the first storm. It dropped about 1.5 meters of snow on us. And about 4 hours later, a second storm came in and dropped another 1.5 meters on us. So we were only able to get measurements at one point. Here we are going out to our cargo line, looking at digging out our equipment. Maybe the contrast here isn't great. We're using sleds to kind of propel ourselves across the surface because the surface was so soft you just sink in. And we only got measurements in one location. This would have been April of 2015. We were able to go back in August and get more measurements at more locations, and we're still again waiting for those results to come back. The good thing about the snowstorms when it's actually precipitating in southeast Greenland is that it holds back the katabatic winds. So on the ice sheets, you have this cold air that sits on the center. It wants to flow out. So on the edge of the ice sheets, you almost always have katabatic winds. They're about 15 knots. But when you have a storm that comes in, it holds back those katabatic winds, and then all that cold air wants to flow off. So we had about 3 meters of snow fall on us over about 5 days, and then it all blew back in our face for the next 6 days. And we basically stopped science, and all we did was dig. And now you can actually see the surface after all that snow accumulated and then blew back. We actually had to construct these little blue things that are in front of the doors of our tents that were working as sort of like snow fences, so we could get a few hours of sleep before we'd have to dig out again, and we could still get out of our tents. So we finally got out. You'll note the helicopter landed. In Greenland, we do go in and out with helicopter. You'll note that it doesn't have its feet on the helicopter. As soon as the helicopter landed, it sunk right into the surface. That scared me quite a bit, but it was able to pull us out, and we came out with our first measurements of that aquifer. Just for the future, we do blogs, usually through Earth Observatory. We'll be going back again to take more measurements of the aquifer in June, July of this year. So Earth Observatory, there's always blogs up. Also, for Icebridge, There's a NASA mission page. It's really good. There's lots of content, videos, a lot of the videos that I've shown on there, pictures from the campaign. There's a Twitter account at NASA ICE. And as that mission ramps up in March, there'll be press releases and a lot of social media outreach on that. So during the COP15, the Paris meetings on climate, NPR in the morning was doing a series of reports, and this one really struck me. This guy, Chris Crockett, he's a planner for Philadelphia Water Department, and he said, what you really want to know is how high it'll go. When you suddenly say the past doesn't predict the future, you're left acting like a stockbroker. And this really spoke to me because we have all these changes going on the ice sheet. We're learning things in real time as observationalists, and it'll take a little while to get those into the models. But the real question is how high will it go? And when the planners are experiencing these 50-year, 100-year events, every few years, they're saying, hey, what should we do? And I said, well, maybe we're not quite stockbrokers, or if we are, we might have a little bit of insider trading. And what can we actually learn from the very far past? And there was this recent report in Science by Dutton, and I really liked this graphic. And what it shows is at the top, the temperature, and we're going from present, and as you go to the right, you're going back in time. And it shows sea level rise from the ice sheets. And it also shows your carbon. The little green circles are your CO2 parts per million. And you can see that sea level right now is quite low. And if you go back in the past, when temperatures were just a degree higher, we had about 6 to 9 more meters of sea level rise. And again, these are from the geologic record. And if you go back to 2 degrees, 1 to 2 degrees, 400,000 years from now, or before present, sea levels were 6 to 13 meters higher. Well, what we know is that sea levels are going to rise. The temperatures in the Arctic have risen, and especially in Greenland, we're going to see that increased sea level rise. What I also like about this graph is that it shows Greenland and Antarctica and how much of Greenland and Antarctica in red at the different stages of sea level, how much they think was contributed from each ice sheet. And what you also see in this is that Greenland is going to consistently contribute more to sea level rise. That when we talk about large amounts of sea level rise, it's going to come from Greenland. It's going to come from Greenland first. And I also like when they show the little wedge coming out of Antarctica, they've actually tilted that towards West Antarctica, and that's actually the region where we will see that sea level rise come out, is in that western portion. They probably should have tipped that the red thing around Greenland about 90 degrees, because it'll probably come from southern Greenland first, and then up. But we're projecting about 1 meter of sea level rise in the next 100 years. And when we look back at past sea levels, that's not really an extreme amount. The real questions we're going to be asking as a scientific community, as a glaciology community, I think in the next few years, especially for Greenland, is where's the water? How is it melting? How is it flowing through the ice sheets? How is that water, is it evacuating quite quickly? On the west coast of Greenland, it appears to be evacuating quite quickly and causing sea level rise. On the east coast of Greenland, there seems that there might be a little bit of a delay function. And what to expect? So just to sum it up, we're going to see large increases in Greenland's contribution to sea level rise in the next decade, and some increases with Antarctic. It's due to the increased warming temperatures at the pole. And you're going to see some scientific debate. We've just discovered a lot of this water, how it's routing through the Greenland ice sheet. So you'll see this scientific debate on how it's being routed and what that means for the ice sheets probably in real time in the next decade. Questions?
Well, thanks so much for your presentation. We have time for questions in the room here, and we also have time for questions for those of you watching online. I just have a quick one to start everything off. Laura, we've seen in the satellite record over the last several months and even the past year, about 2015 being the warmest year on record, month after month after month, temperatures being well above average and setting records. But you see in the global visualization of temperature anomalies, this little blue cold anomaly right off of Greenland. And I was wondering if you could talk about that a little bit.
Yes, and so it is definitely a little bit outside of my area of expertise, because certainly those models are integrating many things that are going on with the atmosphere and the ocean. What we can say from the ice sheets is that we likely have an increase in, and remember those are surface temperatures, so it's the water that's sitting at the top of the ocean. The ocean has a stratified temperature profile, but we do know that Greenland has been losing more mass from meltwater, and that would likely add or contribute to a fresh water, cold fresh water sitting on the top of the ocean. Now, we haven't tied all of that, but what we can say is, again, Greenland is losing more water mass into the ocean in that region.
Thank you. Cheryl, have an online question?
Yes, this is Cheryl with Storm Center Communications, and this question comes from our live stream. And he asks, as to Greenland, are there any changes in black carbon? Also, has soot been detected on Greenland?
Yes, and so that's very interesting research. So soot is certainly detected in Greenland. They talk about, the forest fires, the increase in fires that Dr. Brown talked about this morning, that soot can come and get deposited on the Greenland ice sheet. The Greenland ice sheet, there have been studies, they're showing that it is definitely darkening. It's darkening from both, you could think of the soot and fire inputs, those are probably a little bit less than maybe even in the past, but probably the majority of what's causing it to darken is just that increased melt. That increased melt changes the snow surface, it reduces the albedo. So when we went back to the very, very beginning, we want the poles to stay cold and white. Greenland certainly is darkening, and soot and black carbon are a portion of that, but the actual melt itself is a portion of that too.
Jim Gandy at WLTX in Columbia, South Carolina. The rate at which the ice is melting changes, and obviously not all that water goes immediately into the ocean. How is this complicating future projections of sea level rise?
So I think there's two things you can talk about, right? So yes, some years you have high melt years, and other years you have less. And so when we talk about that is that sort of variability. But we definitely see that the mean state is sort of increasing. And I didn't show the animation, but when we think about that mean state of increasing, that Greenland, in the pictures I showed of the red, the red of where it's melting, that started in the 1970s with just the very edges melting, and now that is steadily increasing inland. And when we talk about the long-term projections, yeah, we'll have high melt years, we'll have less high melt years, but it's really that gradual change that's occurring. And over the long term, we know that more melt is coming off the Greenland ice sheet. That again, we're talking about melt now, but there's also that ice dynamics component, and they do feed back to each other. But the ice has been slow, has been getting faster and faster and faster on that curve. So it's both of those things that when we talk about those sea level projections, that the models are capturing that and working to capture that, and not really that year-to-year variability.
Jim White, University of Colorado. Thanks for the great talk, Laura. I'm as someone who's worked on ice sheets for a long time, I think one of the really important take-home messages from what you've shown is that there's still important new dynamics and physics we need to learn about these ice sheets. I think discovery of these basically groundwater aquifers in the firn ice barrier is really important, because it means that the models that we've been incorporating and using for predictions are missing some important pieces. And we've always known that. But you know, one of the things to recognize is those models won't get any better unless we keep going back and keep doing this kind of work. So and I think that's an important message.
Yes, and it is an important message, and we're just observing it, so it's going to take a while to get into the models. I'll also point out, though, that when we first showed some of the aquifer results in Greenland, one of the modeling groups came to us and said, our model's been storing liquid water in Greenland in that region. And so the models were starting to do it. They weren't doing it at the right amounts or the right depths, but it is important that the models weren't completely wrong in this case. It's just we didn't actually assume that it would be there until we drilled into it.
Following up on that, I'm Jennifer Francis from Rutgers University. You mentioned the expected or projected sea level rise by the end of the century being about 1 meter, and that's about the middle of the road. But it seems like every time we turn around, we're learning that things are changing faster than we thought, and that 1 meter is, you know, the IPCC reports tend to be quite conservative. You know, the Arctic's warming faster. We're seeing these new melt processes you're discovering. Do you really think that 1 meter is still the middle of the road?
You know, I still do, because, again, the IPCC is I think, at about 0.8. It's still a little off that. The models are always going to be more conservative than the observations, because the observations inform the models. I still think that 1 meter is pretty good for now. And to go beyond that, I'd really need to see these processes in the models and see how they play out. Because the other important thing is these are very complex systems. So any one measurement does not tell the whole story, and we need to get that whole story put together in the models before we can really, I think, make that a lot higher.
Lora, this is Dave Jones. I have another question for you about Operation Ice Bridge. What's the plan for going out into the future? Are you planning on observing the Greenland ice sheet via aircraft for the next 5 years, the next 10 years, until IceHack comes up? What's the plan?
Yep. So Ice Bridge has always been a bridging mission. So once IceSat-2 launches, we will have one full campaign under both Greenland and Antarctica with the satellite in the air to make sure that, again, we're trying to reconstruct that record. We don't want to have a gap in our record, and we want to make sure that what we learned from IceSat, we continued with Ice Bridge, and we can apply it to IceSat-2, and we don't have any gaps or and we have a full understanding of how those measurements overlap. So that we can have a very accurate view. Once IceSat-2 launches and we're confident that we understand the data quality between them, Operation Ice Bridge will stop. That said, NASA has a new mission that just started called Oceans Melting Greenland. It's also an airborne mission. The OMG is the acronym. And it is really focused on the perimeters and how the ocean is interacting with Greenland. So watch for that, and that's a 5-year mission into the future.
And one last question for you, Matt, and then we'll come over to you after this. Is you have a room full of local television meteorologists, network meteorologists. How would you, what advice would you give them to describe what's going on in Greenland from a science perspective? I mean, we have to keep monitoring it. Greenland is a source for sea level rise. We have some meteorologists from here from Miami who is very much threatened by it. So I think Greenland seems to be like a canary in the coal mine that everybody keeps watching. So what are your core concerns as a scientist that say, man, we need this answer, we need it quick?
Well, I think one of my core concerns, or what makes Greenland both an exciting place to watch, is that, we talked about in that 2007 to 2009 time frame, when we switched from ice dynamics to melt on the surface being the major mass loss. It's a fundamental change. And, we haven't monitored melt runoff a lot. There is amazingly few. There's a handful of stream gauges around Greenland. So in that sense, it's an exciting place to work. I think should tell the public to really care about what's happening there, because it is posed as, the first canary in the coal mines really are the glaciers. They're going to start to tap out on the ice that they have to lose, and Greenland has a lot of ice to lose. So we should really be monitoring and watching what happens with all that melt runoff.
Matt Safino, KGW Portland. Is there a date, or at least a rough date, for when ICESat-2 will be launched? And is it a NASA launch or a SpaceX launch?
Ooh, it's a NASA launch. It will be November of 2017, I believe, is the current launch date. Go to their the ICESat-2 website, and they keep you updated on that. The instrument's built, and they have pictures and everything of that satellite coming together.
Laura, thank you very much. We really appreciate your presentation, the interactive discussion. And I do also want to remind everyone that coming up in just a few minutes, we'll be bringing back Dr. Lora Koenig and also Dr. Tim Brown to answer any questions that you may have online. Sometimes these sessions last a few minutes, sometimes they last a half hour or so. It really all depends on the questions coming from you online. And please join us back here tomorrow. Tomorrow morning we'll have Dr. Phil Klotzbach, who's from Colorado State University. He's going to talk about seasonal forecasting. You may have seen Phil at times appear on the Weather Channel. And also Lance Rothfuss, who is the Deputy Director of the National Severe Storms Lab. Lance is going to talk about the 2015 severe weather season, and also what kind of technologies are emerging that will help us to be warned faster and further out into the future based on model output and some exciting research that's being done there at NSSL. NSSL is really a gateway into operations, if you will, to the National Weather Service. So this should be a very exciting and dynamic discussion. So please join us back here in about 5 or 7 minutes or so, and we'll have Dr. Koenig and Dr. Brown to answer your questions. Thanks so much, and we'll see you soon.